Here is a number worth sitting with for a moment. 4.2, 4.2 light-years to the nearest star, Alpha Centauri, our closest neighbor in an otherwise empty ocean. Light covers that distance in 4 years and 2 months, traveling at 300,000 kilometers per second, fast enough to lap the Earth 7 times in a single heartbeat. On a clear night, looking south from the right latitude, you can see Alpha Centauri with the naked eye. It glows steadily, orange-gold, like a companion campfire glimpsed across a dark valley. It has been there, burning for the entire history of human civilization. We have been looking at it for thousands of years. In all of that time, we have not sent so much as a photograph in its direction. Our fastest spacecraft, the Parker Solar Probe, moves at roughly 700 kilometers per second at its peak, faster than anything humans have ever built. At that speed, a trip to Alpha Centauri would take about 6,000 years. We launched Parker in 2018. It would arrive sometime around the year 8000, and Alpha Centauri is the nearest star. There are 400 billion more in this galaxy alone. Most people, when they hear numbers like these, file interstellar travel under science fiction and move on. That's a reasonable response. But it skips something important, the question of whether interstellar travel is possible at all, not just fast, but possible, has a real answer. It's not a comfortable answer, but it's more interesting than silence. Let's start with 3 hard facts. Not guesses, not projections. Constraints that emerge from the structure of physics itself. First, there will never be an energy source more powerful than nuclear energy available to human technology. This isn't pessimism or lack of imagination. It's the result of examining every energy scale accessible to matter and finding nothing beyond it. Every chemical reaction, every nuclear process, every field interaction we can manipulate has been surveyed well enough to know what it contains. And nothing in that map outranks the binding energy of atomic nuclei. Some people hope for a discovery that overturns this, some unknown force, some overlooked interaction. Hope is not a method. Second, no object built by human hands will ever cross interstellar distances at more than about 1% of the speed of light, possibly a few percent in favorable conditions. People routinely mention 10%, 20%. Those numbers come from thinking about propulsion without thinking about what it actually requires to achieve it. The moment you apply quantitative constraints, the mass you need to move, the fuel you need to carry, the energy you can extract from that fuel, the number drops to 1 or 2%, not 10. Third, no living human being will ever leave the solar system. These 3 statements taken together seem to end the conversation. They don't. They redirect it. Because when you clear away the science fiction, the warp drives, the generation ships, the heroic crews eating rehydrated food and arguing about the mission, what remains is something stranger and more serious. A real engineering problem with a real, if difficult, solution. One that doesn't look like any story we've told about it. The question changes from how do we send people to the stars to what is actually worth sending, and can it survive the journey? Those are tractable questions. To understand what's possible, you have to understand energy. Not in a vague sense, in a precise, quantitative sense. Because interstellar travel is, at its core, an energy problem. Everything else, the ship design, the navigation, the cargo, is secondary to how much energy you can extract from how much mass. Here is the fundamental relationship. Einstein gave us E equals mc squared. That equation says that mass and energy are interchangeable, and the conversion factor, c squared, the speed of light multiplied by itself, is enormous. A single gram of matter contains roughly 90 trillion joules of energy in its mass alone. The sun derives its light from this conversion. Nuclear weapons exploit a small piece of it. Every energy technology in human history has tapped into it to varying degrees. Now, burn a gram of chemical fuel, a gram of kerosene, hydrogen, whatever you like. The energy you release is roughly 10 to the negative 10 times that gram's rest mass energy, meaning you're extracting about 1/10 billionth of what's theoretically available. Chemical reactions rearrange electrons between atoms. They don't touch the nucleus. They leave 99.9999999% of the available energy untouched. This is why rockets are so large. A Saturn V, the most powerful launch vehicle ever built, weighed about 2,800 tons fully fueled. Its payload to the moon was about 45 tons. The ratio of fuel to useful cargo was roughly 60 to 1. All of that mass, the towers of kerosene and liquid oxygen, existed to move 45 tons a few 100,000 kilometers. And chemical propulsion is already good for its class. There simply isn't more energy available in molecular bonds. Now fission a gram of uranium, the energy released is about 10 to the minus 3 times mc squared, 1,000th of the total mass energy. That sounds small, but compare the numbers. 10 to the minus 10 for chemistry, 10 to the minus 3 for fission. The ratio is 10 million. 1 gram of uranium contains 10 million times more accessible energy than 1 gram of chemical fuel. This is not an incremental improvement. It's a different category of capability. Fusion, hydrogen bombs, the process that powers the sun, does better still. When hydrogen nuclei fuse into helium, roughly 4 times more energy is released per unit mass compared to fission. 4 times might not sound impressive after 10 million, but in engineering terms, a factor of 4 is enormous. It's the difference between a viable mission architecture and one that barely fits in the numbers. The reason we can't simply build a fusion-powered spacecraft is that we don't know how to control fusion. The sun controls it through gravity, 100,000 kilometers of plasma pressing inward from every direction, maintaining the conditions for sustained nuclear burning at the core. We have no access to gravitational confinement at that scale. Magnetic confinement in machines like tokamaks has been under development since the 1950s, and controlled fusion power remains, as it has for 70 years, 30 years away. That may change. But it hasn't changed yet, and we can't build a mission plan around it. What we can do is use fission bombs. The Orion project, studied seriously in the United States in the late 1950s and early 1960s, proposed propelling a spacecraft by detonating a series of nuclear bombs behind a heavy blast plate. Crude, wasteful, deeply uncomfortable in concept, but it would have worked. The engineers who ran the numbers showed it could reach a few % of light speed. It was politically killed by the Partial Test Ban Treaty of 1963 and has never been revived. There is one energy source that theoretically beats everything else: matter-antimatter annihilation. Bring matter and antimatter together and they convert completely to energy. The efficiency is 100%, nothing left over. A gram of antimatter meeting a gram of matter releases the full energy of both grams via mc squared, 1,000 times better than fusion. An engine running on antimatter would be the most powerful propulsion system physically possible. The problem is manufacture. Producing a single gram of antihydrogen would require more electrical energy than the entire planet generates in several years, and the waste heat from the process would be catastrophic for the environment. Particle accelerators produce antiparticles by the handful, measured in nanograms over years of operation. Antimatter propulsion is not a technology being held back by lack of will or investment. It is physically possible and economically absurd by any timescale we can contemplate, so we work with fission, uranium. And from the energy density of uranium, from careful analysis of the thermodynamics of propulsion, a number emerges. The physics of rocket propulsion has a deep constraint built into it. To accelerate a ship, you throw mass backward. The thrust you get depends on how fast you throw that mass and how much of it you throw. These two quantities trade against each other in a way that produces an optimal point. an exhaust velocity that maximizes the speed of your ship for a given amount of fuel. Go below that optimal exhaust velocity, and you run out of propellant before you've used your energy efficiently. Go above it, and you've put energy into your exhaust that you can't recover. The optimal exhaust velocity, it turns out, is roughly equal to the speed the ship itself is trying to achieve. And that speed, for a nuclear reactor with a realistic efficiency of around 25%, works out to about 4% of the speed of light, 4% of light speed to Alpha Centauri in about 100 years. That number sounds almost within reach. 100 years is long, but it's a time humans can conceptualize. It's the span of a century, the distance between a great-grandparent and a great-grandchild. Not comfortable, but imaginable. The number is misleading. Reaching 4% of light speed in principle is not the same as doing it in practice. The constraint isn't energy availability, it's heat. Every nuclear reactor, however efficient, produces waste heat. The heat that isn't converted to useful work has to go somewhere, on Earth. Reactors dump it into rivers and cooling towers. In space, there is no water, no air. The only mechanism for shedding heat is radiation. Hot surfaces emit infrared light, and that light carries energy away into the void. It's the same process by which the Earth cools itself, the same process that makes a piece of iron glow red when heated. In space, radiation is the only heat sink you have. Now, to accelerate a ship of a few hundred tons quickly, briskly enough to reach interstellar velocity in a reasonable time, you need roughly 10 gigawatts of thermal power output, 10 billion watts. That's the combined output of about 10 of the largest nuclear power plants on Earth, all at once. To radiate that much waste heat from surfaces at a temperature of around 1,000 Kelvin, hot enough to glow faintly in the infrared, requires roughly 10 hectares of radiating surface. 10 hectares is 14 football fields. Those radiators alone, built from the lightest materials available, would weigh hundreds of tons. And now you have to accelerate the radiators too. To accelerate them, you need more fuel. More fuel means more mass. More mass means more power needed to accelerate it. More power means more waste heat. More waste heat means larger radiators. The system feeds back on itself and becomes unmanageable very quickly. This is not a detail. It is the central constraint of nuclear propulsion in space, and it's the reason why the bold numbers, 10% of light speed, 20%, dissolve on contact with the thermal physics. You simply cannot radiate heat fast enough to run a powerful enough engine to reach those speeds. The way around it is patience. Instead of burning fuel hard and fast, you burn it slowly and continuously. A low-thrust engine running not for days but for decades. The power requirement at any moment stays modest. The radiators stay small enough to be manageable. The acceleration is barely perceptible, less than a millionth of Earth's gravity, and the journey lengthens. But here is something counterintuitive. Doubling the journey time doesn't double the difficulty. It reduces it by a factor of 10, 20, sometimes 100. Every component shrinks, lower power output, smaller radiators, less propellant consumed per unit time. The engineering goes from impossible to merely very hard. Halving the speed requirement reduces the fuel mass by a much larger factor because of the exponential nature of the rocket equation. Time is the most valuable resource in interstellar propulsion. Spending more of it makes everything easier. Run the equations carefully for a ship traveling at continuous low thrust, optimizing the acceleration profile, accounting for the mass ratio between propellant and payload, applying realistic efficiencies to every component. And here is the result. A ship capable of carrying 200 tons of final payload to a target 30 light-years away, decelerating to a stop at the destination, moving with realistic nuclear power output, takes somewhere between 4,000 and 5,000 years. Choose 5,000 years and the engineering requirements relax considerably. Lower power, smaller radiators, more payload arriving intact. Choose 4,000 years and you're pushing against the thermal constraints. 4,000 years, 5,000 years. Most people hear those numbers and stop listening, but before stopping, it's worth asking the right question. The question is not, can a human tolerate a 5,000-year journey? No human can. The question is, can a machine function for 5,000 years? Can a biological cargo survive 5,000 years? Those are different questions and they have different answers. But first, why go at all? What is worth sending 5,000 years across the void? To answer that, you have to take a detour through biology. Earth is about 4.5 billion years old. Life appeared remarkably quickly, within the first half-billion years. Once it appeared, it spent roughly 3 billion years as essentially nothing. Single-celled organisms, mostly bacteria, colonizing the seas and doing very little that a casual observer would call interesting. Then, roughly 600 million years ago, something changed. Multicellular animals appeared. Bodies with specialized organs, nervous systems, eyes, mouths, complexity suddenly. But trace the history of life carefully, and what you find is a series of bottlenecks, moments where the evolutionary path narrowed to almost nothing, where the future of complexity on Earth hung on improbable events. The emergence of the eukaryotic cell, the kind of cell with a nucleus, the kind that all complex life is built from, appears to have happened exactly once in 4 billion years, from a merger between two different types of bacteria so unlikely that it probably should not have happened. Sexual reproduction, once. Multicellularity, independently a few times, but each time only barely. The nervous system, the eye, consciousness. And here is the part that should give you pause. The sun will brighten over the coming billions of years as it ages. Earth's biosphere has roughly another billion years before rising temperatures make it uninhabitable. Complex animal life on Earth appeared roughly 600 million years ago. That leaves less than a billion years remaining. A window that, if our planet had been slightly less lucky at a few critical junctures, would have elapsed before anything like us appeared at all. We got here with time to spare, but not much. This is not a fringe view. It emerges from careful work by evolutionary biologists studying the history of life's complexity. And it has a strong implication. Life, wherever it exists, is probably rare. Not because the universe is inhospitable, it isn't by any evidence we have, but because the sequence of improbable steps required to go from a self-replicating molecule to a creature capable of asking questions is so long and so unlikely at each stage that completing it requires an extraordinary run of luck. If this is true, and the evidence points that way, though it isn't certain, then the galaxy is populated very differently than the optimistic view suggests. Not full of civilizations, not even full of complex life. Instead, full of planets with the right conditions, orbiting stable stars with liquid water and reasonable chemistry, sitting empty, not barren, potentially fertile, waiting. A habitable planet that is empty of life is not a minor thing. It is an extraordinary waste of potential, sitting in the dark for billions of years until its star expands and sterilizes it. Life that appeared there might, given enough time, eventually produce something that wonders about the universe and its own place in it. But given enough time is the constraint. Time runs out. If you could send life to such a planet, seed it, give it a start, you would be doing something with no parallel in human experience. Not discovery, not colonization, something more fundamental. You would be giving a world the chance it never got on its own. This is why the payload matters more than the propulsion. This is why the question of what to send is, in some sense, the deepest question in the whole enterprise. What do you send? Not people. The energy required to support a living human across interstellar distances, food, water, air, radiation shielding thick enough to protect fragile human biology in real time, makes the mass budget impossible. A crude ship capable of sustaining life for thousands of years would need to be so massive that no nuclear engine we could build could move it. We established this at the beginning. No human will leave the solar system. But life is not the same as a living human. Life in its most compact and durable forms is extraordinarily small. A bacterial spore, the dormant armored form that bacteria adopt when conditions become hostile, is a few micrometers across, smaller than a red blood cell. It contains a complete genetic program capable of rebuilding a functioning organism when conditions allow. Bacterial spores have been revived from amber 30 million years old. They have survived conditions that would kill anything larger almost instantaneously. Seeds, the plant equivalent, are similarly compact. A seed contains not just genetic information, but a supply of nutrients, a developmental program, and a protective coat. Some seeds have germinated after thousands of years in dry storage. The date palm from a 2,000-year-old seed found near the Dead Sea grew into a healthy tree, frozen embryos. This is where it gets interesting for the question of sending complex life. In vitro fertilization produces embryos that are routinely frozen and stored, sometimes for years, then thawed and implanted successfully. The embryo's cells during freezing are essentially suspended, metabolism stopped, time paused. Revived, they develop normally. The payload of an interstellar ship carrying life would be a compressed library of biology, not a zoo, not living animals in cages. Something much more compact, genetic material in its most stable and durable forms. Frozen embryos of as many species as can be included. Bacterial cultures representing essential ecological functions, nitrogen fixation, decomposition, the invisible machinery that makes soil work, spores and seeds, engineered microorganisms designed for specific tasks, if such things exist by the time a mission is launched. The question of what ecosystem to include is itself a research field waiting to be born. Because you can't just send the animals, you need everything that supports them. And some of what supports complex life is counterintuitive. Viruses, for instance. Viruses are the invisible drivers of evolution. They carry genetic material between organisms. They impose selection pressure. They mediate the competition between hosts and parasites that pushes life to become more complex. An ecosystem without viruses would not be a cleaner ecosystem. It would be a stagnant one. Evolution would slow, perhaps stop. You would need to send the viruses, parasites, similarly. An ecosystem without parasites is an ecosystem without one of the primary mechanisms of selection. Parasites kill the weak, spare the strong, and force hosts into evolutionary arms races that produce exactly the kind of diversity and complexity that we associate with life doing well. Whether to include parasites in a biological payload is a genuinely hard question, and no one has worked out the answer yet. These questions, how many species in what proportions representing which ecological roles, are not idle speculation. They are solvable, given the right research program. Biology knows enough to begin thinking about minimal viable ecosystems. We simply haven't had the reason to work on it seriously. Give us the reason and we would. The payload would also carry artificial intelligence. Not because AI can replace biology, it can't, but because something has to be awake during the journey. The biological cargo will be frozen. The reactor and engines will run themselves. But decisions will need to be made. The ship will need to navigate precisely. Arriving at a stellar system after 5,000 years requires extraordinary accuracy over that baseline. Targets will need to be assessed on arrival. The ship needs to survey the destination system, identify candidate planets, characterize their atmospheres remotely, decide where to attempt deployment, then execute the landing sequence, handle the failures that occur in any complex system, and manage the initial stages of biological establishment. None of this requires consciousness. It requires reliability. And reliability over millennia is a solvable engineering problem, as we'll see. Now, how do you build a machine that functions for 5,000 years? This question sounds like the end of the discussion, but let's examine it honestly. The objection, no machine can work for 5,000 years, is usually stated as a fact. It isn't. It's an assumption that confuses. We have never built such a machine with such a machine cannot be built. These are not the same statement. We have never built a machine designed from the start to last 5,000 years, under conditions radically different from anything on Earth's surface, with 5,000 years to do its work. We have built machines designed to last a few decades and watched them last longer than expected. Voyager 1, launched in 1977, is still functioning. It left the solar system in 2012 and continues to transmit data from over 20 billion kilometers away. Its thermoelectric power source has degraded as expected. It's now producing about 40% of its launch power, but it works. After nearly 50 years in conditions far outside its design parameters, the machine works. The challenges for an interstellar ship are different in kind from Voyager, but let's go through them. The reactor first. A nuclear fission reactor running for 5,000 years faces a refueling problem. Uranium burns down. In terrestrial reactors, fuel rods are swapped out every few years. In space, you can't stop the ship and call a maintenance crew, but consider the geometry of space. In zero gravity, there is no structural reason why fuel rods need to be short. You could fabricate fuel rods from highly enriched uranium in lengths of hundreds of meters, kilometers even, and carry them in long spools alongside the ship. They weigh nothing in space. They impose no structural load. The active zone of the reactor is compact. To refuel, you simply motor the long rod slowly through the active zone, millimeter by millimeter, year by year. Fresh material enters from the coil. Spent material exits and trails behind. No mechanical intervention, no refueling in any conventional sense. Just the slow, continuous consumption of a very long fuel element. With sufficiently enriched uranium and a carefully designed burn-up rate, a rod of reasonable length could sustain the reactor for the entire journey. The engineering details are complex, and the details matter. Uranium undergoes fission product buildup that poisons the reaction and requires careful management. The geometry of the rod must be designed to maintain criticality as it progresses through the active zone. But these are problems of reactor physics, not fundamental obstacles. They have analogs in existing reactor designs. Getting electricity from the reactor is the next challenge. The simplest option is thermoelectric conversion, the same principle used on Voyager and every deep space probe. Two dissimilar materials held at different temperatures generate a voltage. Simple, reliable, no moving parts. The problem, efficiency is poor, around 10%, and thermoelectric materials degrade over time as atoms diffuse across the junctions between materials, a process called the Kirkendall effect. At room temperature, this diffusion proceeds slowly but inexorably. Over decades, the junctions blur. Over centuries, they'd be gone. But here's what saves us. Diffusion rate is exponentially sensitive to temperature. The formula governing it has temperature in the denominator of an exponent, meaning that as temperature drops, diffusion rate collapses far faster than linearly. At the operating temperature of deep interstellar space around 20 degrees Kelvin, 20 degrees above absolute zero, the diffusion rate is suppressed by millions or billions compared to room temperature. A thermoelectric converter that would degrade to uselessness in a century at room temperature would function essentially unchanged for millions of years at 20 Kelvin. The electronics controlling the ship face the same analysis and reach the same conclusion. The transistors, the logic circuits, the memory, all of these depend on precise atomic scale structures that diffuse at room temperature and effectively freeze at cryogenic temperatures. The cold of deep space is not just an inconvenience to be managed. It's a preservation mechanism of extraordinary power. There is another option for power conversion, a turbine. A heat engine in the most classical sense, steam or gas or some working fluid, heated by the reactor and expanded through a turbine to generate mechanical work, which then drives a generator. Turbines are not solid state. They have moving parts. People instinctively assume moving parts fail. But the question is, why do they fail? They fail from material fatigue, from corrosion, from thermal cycling, from lubrication breakdown in deep space. No corrosion, no atmosphere to corrode with. Thermal cycling is minimal. The ship operates at near constant temperature for millennia. Fatigue depends on load cycles and stress levels. Both can be designed to very low values in a system with small continuous forces rather than large intermittent ones. Lubrication in vacuum can be achieved through self-lubricating materials or magnetic bearings. Jeff Bezos funded a clock designed to run for 10,000 years. It lives inside a mountain in West Texas, carved into the rock, powered by thermal differentials between day and night. Engineers analyzed it seriously and concluded it would work. Its gears and escapements, purely mechanical, no electronics, will keep time for 10 millennia. If clockwork can be engineered for 10,000 years in a Texas mountain, a low-speed turbine in the benign environment of deep space is not obviously harder. The ion engine, which converts electrical power to thrust by accelerating ionized propellant, is mechanically simple. There are no pistons, no combustion chambers, no valves in the conventional sense. Ions are extracted from a plasma, accelerated through an electric field, and expelled. The main wear component is the electrodes from which ions are extracted. They erode slowly over time. With appropriate materials and redundant systems, ion engines have operated for tens of thousands of hours in space already. Scaling to millions of hours requires engineering and testing, but not a change in the underlying physics. The ship as a whole will look nothing like science fiction. There will be no streamlined hull. There's no air to be streamlined through. There will be no viewing windows, no corridors, nothing designed for human comfort or human perception. There will be a nuclear reactor, separated from the rest of the ship by kilometers of tether, because distance is the most effective radiation shield you have, and in space you can make it as long as you need it. The engine module will be at one end. The payload module, reactor waste heat radiators, the frozen biological cargo, the AI systems at the other end. Between them, tether and vacuum. The whole assembly will look, at a distance, like something strung between 2 points on a very long line. The thrust will be about 2 kilograms, roughly the weight of a house cat, maintained continuously for centuries. The acceleration will be so small that a dropped object inside any habitable module would take minutes to drift a meter. But continuous small thrust over centuries adds up. That is how you cross 10 parsecs. The cargo needs protection. And here the problem becomes subtle. Deep space is not empty. It is pervaded by cosmic rays. High-energy particles, mostly protons, accelerated to near light speed by supernovae and other violent events scattered across the galaxy. These particles carry enormous energies. They pass through ordinary matter as if it barely exists. The shielding that stops a terrestrial radiation source, lead, water, concrete, is essentially useless against the highest energy cosmic rays. They go right through. The obvious solution, piling on more shielding, doesn't work for 2 reasons. First, the mass required to stop high-energy cosmic rays through pure absorption is enormous. You'd need hundreds of meters of water equivalent, which is hundreds of thousands of tons. Second, when a high-energy cosmic ray hits a nucleus in your shielding, it doesn't just stop, it produces secondary particles, a shower of pions and muons that spray through the material and do their own damage. Sometimes the shielding makes things worse. The solution is magnetic deflection. The Earth deflects cosmic rays using exactly this principle. Its magnetic field bends incoming charged particles around the planet, channeling them toward the poles where they produce the aurora. A sufficiently strong magnetic field aboard the ship can do the same thing for the cargo. The specific numbers: a superconducting solenoid, a coil of wire carrying large current, generating a field of around 10 Tesla over a volume large enough to surround the payload module, would deflect incoming protons with energies up to about 20 billion electron volts. That cuts off the majority of the cosmic ray flux. What remains after deflection is reduced by roughly a factor of 50 compared to the unshielded environment. That residual level is approximately what life experiences on Earth's surface. Life on Earth's surface is not sterilized by cosmic radiation. Human beings live entire lives under roughly 15 microrengen per hour, equivalent dose without it being a dominant health concern. Evolution has operated for billions of years under this background. The frozen cargo, dormant, not actively metabolizing, not repairing damage in real time, will accumulate damage over the journey. But the DNA damage rate at Earth-equivalent cosmic ray exposure, integrated over 5,000 years, is within the range that some organisms have already demonstrated they can survive. Worms recovered from Arctic permafrost, frozen for tens of thousands of years, have been thawed and lived normally. Seeds have germinated after thousands of years. Bacteria have revived from amber tens of millions of years old. These organisms' DNA was damaged by cosmic rays during that storage, but the damage was at a level their repair mechanisms could handle upon revival. For complex organisms with longer, more intricate DNA, mammals for instance, the survival rate after cryogenic storage under radiation is lower. Experiments with frozen mouse embryos under radiation show measurable increases in mortality compared to controls. Some embryos survive, some don't. The exact numbers depend on the dose, the duration, and the repair capacity of the organism. The 5,000-year journey duration, with magnetic shielding reducing cosmic ray flux to Earth surface levels, is in a range where biological survival is plausible but not guaranteed. Longer journeys become progressively harder to survive. This is why the 30 light-year distance appears repeatedly as the practical boundary, not just because of propulsion limits, but because biology limits how long the cargo can be kept frozen under any level of radiation. The superconducting coil requires cold to operate. Superconductors carry current with zero resistance only below a critical temperature. Above it, they behave like ordinary resistors and quickly lose the current to heat. The critical temperature depends on the material. Conventional superconductors require liquid helium temperatures around 4 Kelvin. More advanced materials can superconduct at higher temperatures, though typically with lower critical fields. The good news, deep interstellar space is cold. Far from any star, the equilibrium temperature of an object, the temperature it reaches when it radiates as much energy as it absorbs from the cosmic microwave background and distant starlight, is around 20 degrees Kelvin. This is cold enough for many practical superconductors. The ship doesn't need active refrigeration for its magnetic shielding system. The universe provides. Once the current is established in the superconducting loop, it circulates indefinitely, producing the magnetic field, requiring no additional energy input. The shield runs itself. There's one timing constraint. The superconductor must be activated after the ship has left the solar system and its vicinity, where solar radiation would warm the coil above its critical temperature. This means the cargo is unshielded during departure. The journey from Earth to the edge of the solar system, at low continuous thrust, takes years, possibly decades. During that phase, the cosmic ray exposure accumulates without magnetic protection. The dose during this phase is manageable compared to the 5,000-year cruise, but it needs to be accounted for. There are obstacles people commonly cite that turn out, on examination, to not be obstacles: dust and meteoroids. The intuition says a ship crossing 10 parsecs must inevitably be peppered with debris, particles, and rocks and whatever else drifts in the space between stars. The numbers say otherwise. Interstellar space is extraordinarily empty. A ship with a cross-section of 100 square meters would sweep up roughly 1 gram of dust and 100 grams of gas over its entire journey to 30 light-years. Against the dust, a thin foil shield, perhaps a millimeter of aluminum. The impact energy of a dust grain at the ship's velocity is deposited in the foil and dissipated. Against the gas, negligible. The gas atoms simply pass through or bounce off. What about larger objects? There are interstellar objects, rocks and planetesimals ejected from other stellar systems, drifting freely through the galaxy. We've detected a few, Oumuamua, Borisov. From the statistics of detected objects, you can estimate the density of such objects in interstellar space. The result: the probability of a ship with a cross-section of 100 square meters striking any object larger than a centimeter over a 30 light-year journey is approximately 1 in 10 to the 18th power. 10 to the 18th is a number so small it has no everyday name. A quintillion? Something in that range. The probability of being struck by a genuinely hazardous object is, for practical purposes, 0. The film Passengers depicts a ship being struck by an asteroid large enough to cause catastrophic damage. For a journey of a few dozen light years, this event has a probability of around 1 in 10 to the 16th. This is not a risk that needs to be engineered around. It is noise, semiconductor degradation from atomic diffusion, the Kirkendall effect. This concern is real at room temperature, where it degrades thermoelectric devices and semiconductor junctions over decades. At 20 Kelvin, the diffusion coefficient falls by factors of millions. The electronics that would degrade in a century at room temperature will function unchanged for geological timescales at cryogenic temperatures. The cold of deep space eliminates this failure mode. Fuel burn-up fractions. Current reactors burn only about 10% of the uranium before it must be removed. The buildup of fission products poisons the reaction. For a mission lasting thousands of years, you need to burn much more. This is a reactor design problem, and it is a hard one. Highly enriched uranium in fast-spectrum reactors achieves higher burn-up fractions. Breed and burn configurations, in which the reactor breeds its own fissile material from fertile material, can achieve very high fuel utilization. These designs exist conceptually. Engineering them for reliability over millennia is an unsolved problem, but a well-defined one. The objection that no mechanism can work for thousands of years rests on the observation that no mechanism has been designed and built for that purpose. This is true. It's also not evidence of impossibility. It's evidence of lack of motivation. When the Apollo program needed a machine to work for a few days on the lunar surface, machines were built that worked for a few days on the lunar surface. When the Voyager program needed machines to work for decades in deep space, machines were built that have now worked for 5 decades. When a clock was wanted that would run for 10,000 years, engineers analyzed the problem and found a feasible design. The pattern is clear. Machines work for as long as they're designed to work, provided the design is done carefully and tested well. No one has yet designed a machine specifically for a 5,000-year operational lifetime in the conditions of deep interstellar space, with the constraints of the mission we're discussing. No one has tried. Claiming it's impossible without having tried is not physics. It's surrender, dressed up as realism. What does exist within 30 light-years to make any of this worthwhile? More than 300 stars within that sphere. The majority are red dwarfs, small, cool, violent in their youth, prone to powerful stellar flares that irradiate nearby planets with ultraviolet and X-ray radiation. Red dwarfs are not hospitable hosts. Their habitable zones, where liquid water might exist, are so close to the star that planets there are tidally locked, one face eternally baked, the other eternally frozen. The zones where oceans might persist are bathed in radiation from frequent flares. Red dwarf planets may be warm, but warmth alone does not make a world hospitable. We'll set them aside. That leaves roughly 60 stars of more interesting types: yellow dwarfs like the Sun, orange dwarfs somewhat cooler, some slightly hotter than the Sun, 60 possible destinations. And around those 60 stars, statistics say there are planets. The Kepler Space Telescope, launched in 2009 and operating for 9 years, changed what we know about planets around other stars. Kepler watched roughly 200,000 stars simultaneously, staring at a single patch of sky for years and measuring the brightness of each star with extraordinary precision. Every time a planet crossed between its star and Earth, what astronomers call a transit, Kepler saw the star dim slightly. A Jupiter-sized planet dims its star by about 1%. An Earth-sized planet dims its star by about 1/10,000th, 100 parts per million. That is a signal so small that detecting it requires averaging thousands of data points to pull the signal from the noise. Kepler was designed to do exactly that. Over its mission, Kepler confirmed the existence of more than 5,000 planets. But the important result wasn't the count, it was the statistics. Almost none of Kepler's confirmed planets were Earth-like in the relevant sense, roughly Earth-sized, in the habitable zone of a Sun-like star. There were 10, maybe 20 such planets in the entire dataset. Researchers initially worried that this meant Earth-like worlds were rare. Then they asked a better question. If Earth-like planets were common, would Kepler have found them? The answer required injecting simulated Earth-like planets into the Kepler data and checking whether the detection pipeline would catch them. The answer was almost never. The geometry has to be exactly right. The planet's orbit has to be aligned to cross in front of the star from Earth's perspective, which only happens for a small fraction of all orbital planes. The transit has to occur during the observation window, and the signal at Earth size is right at the noise floor for most stars. The non-detections were not telling us Earth-like planets were rare. They were telling us that Kepler was nearly blind to them. When researchers corrected for these biases, extrapolated from what Kepler could see to what actually exists, the fraction of Sun-like stars with an Earth-sized planet in the habitable zone came out somewhere between 15 and 25%. 1 in 4, approximately. In our galaxy, that means roughly 1 billion Earth-like planets. And within 30 light years, the practical boundary of where a nuclear-powered mission might reach, that calculation predicts more than a dozen such worlds, probably more, given the uncertainties favor higher numbers. We haven't found them individually. The tools to directly characterize nearby Earth-like planets don't yet exist. What's needed is a space telescope large enough, with a coronagraph powerful enough, to block the blinding light of a nearby star and detect the much fainter reflected light of an orbiting planet. Then, from that light, take a spectrum, split it into wavelengths, and read the chemical fingerprints of whatever is in the planet's atmosphere. Water vapor, carbon dioxide, ozone, which requires molecular oxygen to form, methane, which would rapidly react away if life weren't continuously replenishing it. These are the signatures of a world that might be alive, or might accept life. These instruments are being designed. The James Webb Space Telescope has taken early steps. Larger, more specialized telescopes are on drawing boards. Within a few decades, we may have spectra of nearby exoplanets good enough to say, this one. This is the target. That moment, when a specific world is identified, characterized, and judged to be both habitable and empty, is when the abstract enterprise of interstellar flight becomes concrete, when a destination has an address. There is a category of question that the engineering doesn't answer. An interstellar mission lasting 5,000 years cannot be funded by a government. Most governments don't survive 500 years. The Roman Empire, one of history's most enduring political entities, lasted roughly 5 centuries in the West. No funding body, no institution, no political structure currently existing can commit to a 5,000-year project. Economic incentives don't work either. There is no return on this investment ever for anyone who invests in it. The fraction of the project's cost that could be recovered in any time scale a market can model is zero. This is not a project that benefits shareholders or voters or even citizens of a country. It benefits, if it benefits anyone at the human scale, the people who launch it in the sense of having done something meaningful, and it benefits at the timescale of the mission, beings who do not yet exist on a world we cannot yet identify. It is a purely altruistic project in the most demanding sense of the word, not altruism toward people you know or can imagine. Altruism toward the universe, toward the possibility that something extraordinary might exist somewhere it otherwise wouldn't. Human history has records of projects like this. They're not common, but they exist. The builders of medieval cathedrals knew they would not see the finished structure. Notre Dame de Paris took nearly 2 centuries to complete. No individual who laid the first stones was alive when the last stones were placed. They built anyway. The medieval European practice of planting oak forests, specifically to provide shipbuilding timber for naval fleets that wouldn't be built for a century or more. Those foresters planted trees they would never see harvested. They did it because there was a civilization that thought on that time scale, and they were part of it. An interstellar mission is that kind of project, but harder. And it will not be done by humanity as a whole. Consensus at that scale is impossible. It will be done if it's done by a sufficiently large, sufficiently funded, sufficiently motivated group of people who share the goal and are capable of organizing institutions that outlast any individual. Not a government, not a company. Something more like the institutions that built the cathedrals, organized around a shared purpose that transcended any individual life expectancy. The project's first phase, identifying a target, doing the science, characterizing candidate worlds, is entirely within the timescale of normal human institutions. It could begin now and produce results within decades. The engineering phase, designing and testing reactor systems, propulsion systems, cryogenic biological preservation systems, AI guidance could follow, and would overlap heavily with applications of those same technologies in the nearer solar system. A nuclear tug that can move cargo efficiently around the outer planets is not a different technology from the early stages of an interstellar drive system. The investment pays off closer to home before paying off far away. The actual launch, committing a ship and its cargo to a 5,000-year journey, requires trusting that the mission will succeed without any of us alive to see it. This is psychologically unusual for human beings. We are adapted to think on timescales of years and decades, not millennia. But the act of choosing to do it anyway, of building something that will outlast us by 5,000 years and do something meaningful at the end of it, that act is perhaps the most characteristically human thing imaginable. Everything that makes human civilization unusual in the biological world is present in it. Foresight, planning, abstract valuation, altruism toward strangers across time. Stephen Hawking, who spent his career at the intersection of physics and the deepest questions about the universe and humanity's place in it, said something worth repeating. Humanity will either genuinely expand into space, not just low Earth orbit, not just the moon, but genuinely out, or it will not survive long enough to matter. Whether you agree with his timeline or his framing, the underlying logic is hard to dismiss. A species confined to a single planet is one catastrophe away from oblivion. The catastrophe doesn't need to be dramatic. It can be slow. It can be a century of bad decisions compounding quietly into irreversible decline. Civilizations can go extinct by becoming less capable of long-range planning, not just by being struck by asteroids. What would it mean to be the civilization that launched life to another star? Not the civilization that discussed it, or funded a feasibility study, or concluded in a report that it might someday be worth attempting. The civilization that actually built the machine and sent it. It would mean that on a world 30 light years from here, which has been sitting in darkness waiting for 5 billion years, something stirs that would not exist without us. Not a human. Something small and strange and patient, a microbe, a spore, a bacterium, doing what life does, which is persist and change and become. Given enough time, that first stirring could become anything. It has no obligation to our expectations. It will evolve by its own logic, under conditions we can't predict, toward forms we cannot imagine. That is the only form of immortality available to a civilization. Not the preservation of any individual or any culture or any idea. Something simpler and more permanent. The continuation of the story. There is a version of this problem that looks exactly like this one, seen from the other direction. Somewhere in this galaxy, around a star that formed several billion years before the Sun, on a planet that had the right chemistry and the right timing, something like us may have asked the same questions. They would have run similar equations. They would have found the same constraints. Energy limited to nuclear, speed limited to a few percent of light, no living passengers, biological cargo only. They would have surveyed the nearby stars and found dozens of candidates. We don't know what they decided. We haven't found any evidence of what they sent, if they sent anything. Maybe the project was too hard, the timescale too long, the will too weak. Maybe that's the answer to what's called the Fermi paradox. Not that intelligence is rare, but that this specific kind of long-range altruism, the kind that commits resources to a project whose results will never be seen by anyone who committed them, is rarer than intelligence itself. Maybe the filter that prevents civilizations from spreading across the galaxy is not a catastrophe. Maybe it's simply that most civilizations, when they do the calculation, look at the numbers and go home. Or maybe the opposite? Maybe what they sent is somewhere in the galaxy right now, a slow machine, still traveling, already arrived somewhere and doing its work. Maybe life is not as rare as we fear, not because it arises spontaneously everywhere, but because some civilization, somewhere, billions of years ago, decided to spread it. Maybe we are ourselves the result of that decision, seeded, not spontaneous. We would not necessarily know. If that's true, then we're not contemplating our first interstellar mission. We're contemplating continuing one that started before the Earth existed. The engineering is understood. The physics is known. The obstacles are real but surmountable. The journey is brutally long, but not physically forbidden. The biological cargo is compact. The energy source adequate. The shielding achievable. Each component of the problem, examined carefully, turns out to have at least one solution. The real constraint is not scientific, it's civilizational. It's whether we become the kind of civilization that can commit to something we won't see completed, that provides no immediate return, that benefits beings not yet born on worlds not yet identified, for no better reason than that it is the right thing to do with the capability we have. Hawking said humanity must go to space or perish. He framed it as a matter of survival, and perhaps it is. But there's another framing. Not survival, but meaning, not avoiding catastrophe, but choosing something to reach toward that is genuinely hard, genuinely good, genuinely beyond the capacity of any single lifetime to complete. A task at the edge of the possible, beyond the span of any human life, carrying forward something irreplaceable. That task reveals what a civilization is made of, not whether it succeeds immediately, whether it chooses to begin. There's a line spoken by a character in a novel about this very project, a novel where the protagonists are sitting outdoors somewhere, slightly drunk, looking up at the sky and talking about something far beyond their ability to finish. One of them says, any task worth doing by its nature has at least one solution. It might have more. We don't know yet. We haven't tried. We might as well start.